In the combustion process, there are some terms which we have to study because whenever we have to analyze the combustion process, so we come across these type of things. Okay, so first process which we call as a complete combustion. Okay, so if the all carbon in the fuel burns to CO2 and all hydrogen burn H2O and all sulfur burns to SO2. Okay, so then it is called a complete combustion. So if anything, you have seen that if there is unburned fuel, for example, if the carbon is not completely burned and it is in the form of the product side, okay, so it's mean it is an incomplete combustion. Okay, so it's mean that if we have carbon, H2O, carbon monoxide, and OH at the product side. Okay, so it's mean it is called the incomplete combustion. However, if these all components turn into some type of, for example, CO2, that carbon changing into CO2, hydrogen changing into H2O, and sulfur turn into SO2. So it's mean it is a complete combustion. If you cannot see in the product side any element like this, like carbon H2O, carbon monoxide. Okay, so it's mean that it is a incomplete it is a complete combustion. However, if you can see these components, so it is called incomplete combustion. So this is the basic understanding that how you judge that this equation is a complete combustion equation or this equation is related to the chemical equation is related to the incomplete combustion equation. Okay, so now coming towards the reason of the incomplete combustion. So there are three main reasons. So first is the insufficient oxygen. So if we have to supply insufficient oxidizer to the combustion process, so it's mean that it will turn out to be the incomplete combustion process. So second thing is that insufficient mixing in the combustion chamber during the limited time that the fuel and oxygen are in contact. Okay, so that is another cause of the incomplete combustion. And also another thing which is the disassociation. Okay, so this term you already know that if we have to just break up the molecules or the atoms into different forms, okay, at high temperature, so this is the phenomenon which we call as a which we decided as a dissociation. Okay, so now coming towards the terms, how you have to judge the incomplete combustion or the combustion, it is a complete combustion. Okay, so for example, this is your fuel, this is your air. So here is a combustion chamber. Okay, so give me 1 minute. I will come back. Okay, so now here for example, if we have the fuel, okay, so this is just for example that if we have a fuel, we have the air, okay, and there is a combustion chamber, and we have produced NCO2, m by 2 H2O. So this is m by 2 just a balanced equation. Okay, so and then there is an excess O. Okay, so for example, in the question it is mentioned that you are supplying some amount of air, and that air is the excess air. Okay, so it's mean that you will get some excess O2 that is just represented in the product side. Okay, and similarly you get the end. Okay, so we will see that how to deal with the excess air type of problems also. Okay, in this lecture also. So oxygen has a much greater tendency to combine with hydrogen than it does with carbon. Therefore, the hydrogen in the fuel normally burn to completion and forming H2. Okay, so this is how we have to deal with the complete combustion. Okay, so we will try to solve problems related to also complete combustion and incomplete combustion. Then you will get better understanding how to deal with this. Okay, so now another term which we commonly use while analyzing the combustion processes is the stoichiometry or theoretical air. Okay, so this term you already, I think, see in your chemistry courses as well. Okay, so theoretical air, basically this is the minimum amount of air needed for the complete combustion of a fuel, and also we referred as a chemically correct amount of air or 100% theoretical air. Okay, so it's mean if it is mentioned in your question, we have a theoretical air. Okay, so it's mean so you have to just judge it that it is we are talking about 100% theoretical air, and it is the minimum amount of air needed for the complete combustion of the fuel. Okay, so in the similar way, we have the theoretical combustion or the stoichiometric combustion, the ideal combustion process during which fuel is burned completely with the theoretical air. So it's mean if we are supplying 100% of theoretical air and the combustion process take place, so it we call as a theoretical combustion process. Okay, so then there is an excess air. Okay, so the amount of air in excess of the stoichiometric amount. Okay, so stoichiometric means the minimum amount which we already required. So if the air is in excess to in comparison to the stoichiometric amount, so usually expressed in terms of stoichiometric air and as percent excess air or percent theoretical air. Okay, so we will see with the help of example also what is the meaning of excess air. Okay, so then there is a deficiency of air. So amount of air less than the minimum amount of air which is required for the combustion, often expressed as a percent deficiency of air. Then the equivalence ratio, the ratio of actual fuel air ratio to the stoichiometric fuel air ratio, we call it as a equivalence ratio. Okay, so now here, if we can just say that, for example, if I just give you the question and I just mentioned that in this combustion, the fuel is burned with the 50% excess air. Okay, so the meaning of this is that it contains 150% theoretical air. So 100% is the air which is required for the minimum amount, which is the minimum amount for the combustion process, and then we are adding 50% in it. Okay, so we call as a 50% excess air. So we have to represent it as a 150% theoretical air. Okay, so similar, if we in the question it is mentioned the air is 200% excess air. Okay, so we just say that it is 300% equal to 300% of the theoretical air. So 100% is the minimum amount and 200% we are supplying excess amount. Similarly, if we just represent at 90% of theoretical air, so for example, if and we need 100% theoretical air for the complete combustion, or we can say stoichiometric amount, that is the minimum air required for the combustion process. So if it is mentioned it is 90%, so it means it is 10% deficient of air. Okay, so similarly, if I say it is 80%, so it means it is 20% deficiency of air. Okay, so this is how you have to deal with when in the problem statement it is mentioned you are supplying excess air and you are supplying deficient air. Okay, so now here, if we can just say that the equation which is related to the complete combustion, so this is mentioned over there. So if we have CH4 and there is air which is as oxidizer, and then we get the CO2, H2O, and N2 on the product side. Okay, so if you can notice that there is no unburned fuel over there. Okay, so we do not see the carbon over there, we do not see H2O alone, we do not see any other product. Okay, for example, we deal with the, we already seen the previous slide also. And also there is no free oxygen in the product. Okay, so if there is no free oxygen, again we call as a complete combustion process. Okay, so this is the one thing which from which you have to easily judge that either it is a complete combustion equation or either it will be a incomplete combustion equation. Okay, so this we already see in the previous slide that what is the complete combustion. Okay, so all the carbon in the fuel to CO2, all the hydrogen to HO2 and H2O and sulfur to SO2. So incomplete combustion, if we have these elements at the product side, so it is called the incomplete combustion. Okay, so now here the incomplete combustion occur even when more oxygen is present in the combustion chamber than is needed to the complete combustion process. And this may attribute to insufficient mixing in the combustion chamber during the limited time that the fuel and the oxygen are in contact. So this we already talked about in the previous slide. Okay, so this We already see some of the carbon, however, and carbon monoxide and just plain carbon particle. Okay, so this we already talked about. Okay, so now here if you can just notice over there, for example, if it is mentioned in the question that the equation for the stoichiometric combustion equation is mentioned like this. Okay, so you can easily say that the product contain no carbon, H2, carbon monoxide, okay, or any other free type of elements, okay, in this equation. Okay, so you can easily say that it's a stoichiometric combustion equation or it is a complete combustion equation. Okay, so this is how you have to judge it. Okay, so now in actual combustion process, it is a common practice to use more air than the minimum amount to increase the chances of complete combustion. Okay, so this we commonly use that we use in the actual combustion process as well to supply more air rather than to supply just a specific amount that is required for the combustion process, so that it will increase the chances of combustion in the combustion chamber. The amount of air in excess of stoichiometric amount is called excess air. The amount of air is usually expressed in terms of stoichiometric air. Okay, so this we already talked about that if we are 50% excess air, it is equivalent to 150%, and 200% excess air, it means it is 300% of theoretical air. Okay, so stoichiometric air can be expressed as 0% excess air or 100% theoretical air. So if it is mentioned 0% excess air, so you easily judge that we are talking about 100% theoretical air, that there will be the minimum amount is present for the combustion. Amount of air less than stoichiometric amount are called deficiency of air and often known as deficiency of the air, percent deficiency of the air. Okay, so this we already say talked about in the previous slide. 90% theoretical air mean 10% deficient of air. Okay, so the amount of air used in the combustion process is also expressed in terms of equivalence ratio, which is the ratio of the actual fuel air ratio to the stoichiometric fuel air ratio. Okay, so if it is mentioned in the question, you have to find the equivalence ratio. So you just have to take the ratio of the actual fuel air ratio. So actual fuel air ratio, basically we are talking about the actual combustion process to the stoichiometric fuel air ratio. It means we have to consider for the stoichiometric equation. Okay, so for both of the air fuel ratio, we have to consider two different chemical reaction equations. Okay, so we will practice also one question so that we will get understanding. Okay, so this is the first question. This is from your book. Okay, so you have to read the statement, then you will try to solve. Okay, so in this question it is mentioned that ethane is burned with 20% excess air during the combustion process. So you are already see that what are the products and what are the reactant involved in this chemical combustion process. So assuming complete combustion and total pressure of 100 kilopascals, so you have to determine the air fuel ratio by using this step. Okay, so first thing is whenever you have to start analyzing the air fuel ratio problem or anything, you have to start with the chemical reaction equation. Okay, so in the exam, I will already I will try to provide all these equations in the problem statement. Okay, so you do not need to remember these equations or where these equations come from. Okay, so for example, I'm just going to write the equation, just the chemical equation for the combustion process. So O2. Okay, so this is Z. Just I will represent one component over there, Z. I will tell you what is this later on. Okay, so this is the combustion equation to CO2, to H2O, Okay, so now here in the question it is mentioned that we have 20% excess air. Okay, so the meaning of this is 20% excess air. It's mean we have 120% of theoretical air. Okay, so you have to just multiply 1.2. Okay, so this is the percentage and you present with the ATH. Okay, so this ATH is basically the stoichiometric coefficient of the air. Okay, so this we will find when we are dealing with the excess air problems. Okay, so in the product also we can just write 1.2 into 3.76. So ATH, which is the theoretical, you can say theoretical stoichiometric coefficient of air, into N2, and similar another product which is 0.2 stoichiometric coefficient into O2. Okay, so this is the complete equation. Okay, so this equation I will provide in each question which is related to the combustion process. Okay, so now by using this relation, this equation, chemical equation, first you have to balance the O2 so that you will get the coefficient which is the stoichiometric coefficient. Okay, so your first thing you have to find from this equation is to find the ATH. Okay, so I will just apply the balance of O2 from the both side. Okay, so it will get 1.2 ATH, which is stoichiometric coefficient, is equal to 2. Okay, so 2 and the product side plus 1.5. Okay, because it's the monatomic oxygen with the H2O, and then plus 0.2 ATH, which is over there. Okay, so now by using this balancing, I can easily find the stoichiometric coefficient first. Okay, so now ATH is equal to 3.5. Okay, so this is the first thing you have to find for excess air problems, or either it will be a deficient air problem as well. Okay, so now the complete combustion equation become C2H6. Okay, so just by put the value of this coefficient in the combustion equation, which I already read before. So 1.2 into 3.5, and then the air O2 plus 3.76 into. Okay, so now this is the combustion equation which become after finding this coefficient. Okay, so this equation will be provided in the problem statement, and this you have to find it by yourself. Okay, after the all the data you have to see in the problem. Okay, so now here our main target is to find the air fuel ratio. Okay, so air fuel ratio we can easily find by using this combustion equation. Okay, so air fuel ratio is m air over m fuel, which we already discussed. That is basically the ratio of mass of air over mass of fuel. Okay, so mass of air. So in the air we have okay, and we can represent with the number of mole of air into molar mass of air over number of mole of fuel and molar mass of fuel. So number of mole of air, which is associated with the, okay, so in this equation you can easily find that 4.2. Okay, so this comes by using the multiplication of this. Okay, into 4.76. So 4.76 comes from 1 plus 3.76. Okay, so this is how it comes from. And then molar mass of air, which you can easily go to table A1, okay, and find that it will be 29 kilogram per kilomole. Similar procedure, you have to find the number of mole of fuel. Okay, so number of mole of fuel. So here we are talking about carbon and hydrogen. Okay, so we have 2 into 12 kg, and plus we have the H2. Okay, and you can say that the 3 into 2. Okay, so now we have the both values, so we can just divide these two things and we will get the air fuel ratio 19.3 kilogram per air per kg of fuel. Okay, so this is the procedure of finding the air fuel ratio if it is mentioned that you are supplying excess amount of air. Okay, so first process you have to find the stoichiometric coefficient in the combustion equation, and then you have to go towards the solution for the air fuel ratio. Okay, so if you have any question, you can ask me, and then we'll move towards the next question.
सर इस एमए आपने कैसे कैलकुलेट किया था, दोबारा बताएं।
किसमें ये एमए
एफ इक्वल टू एमए ओवर एमए।
ये आपके पास इक्वेशन है जो कि एयर फ्यूल रेशियो हम कहते हैं मास ऑफ एयर ओवर मास ऑफ फ्यूल। ओके, अब ओके मैं आपको जो है ना इसको क्लियर करते हैं तो ओके, सो मास ऑफ एयर ओवर मास ऑफ फ्यूल। ओके, तो इस इक्वेशन में अगर आप देखें तो आपके पास एयर क्या है, आपके पास एयर है O2 प्लस 3.76 N2। okay, so this is the standard form of air whenever we have to analyze the combustion process, so we can say it contain 1 kilomole of O2 plus 3.76 kilomole of N2. Okay, so this is the standard. Now from the equation it is mentioned that it consists of how many terms it will be multiplied, 4.2 into O2 plus 3.76 N2. Okay, so this is here you get the number of mole of air. The number of mole of air, molar mass of air over number of mole of fuel, molar mass of fuel. Okay, so now this equation becomes like this. Okay, so clear?
Yes sir.
So it's come from the previous knowledge, so you can go to the previous lecture, you can easily find it that we already talked about that mass is equal to number of mole into molar mass. Okay, so then I just put over there and it turns out to be the equation like this.
सर फ्यूल के नंबर ऑफ मोल्स कैसे फाइंड करेंगे?
ओके, मैं बताता हूँ। ओके, सो फ्यूल बेसिकली हमारे पास है, जब आपने फ्यूल की बात आएगी तो बेसिकली फ्यूल आपके पास है कॉम्बिनेशन ऑफ कार्बन एंड इट विल बी द कॉम्बिनेशन ऑफ H2। ओके, सो कार्बन जो आपके पास यहाँ पे शो हो रहा है, कितने शो हो रहे हैं आपके पास जो रिएक्टेंट साइड पे 2, अगर आप इसको बैलेंस करेंगे तो तब भी आपके पास यहाँ पे 2 किलो मोल आपके पास आ जाएगा कार्बन का। ठीक है, जब आपके पास अगर आप एनालाइज करें इस केमिकल इक्वेशन को, और उसके बाद आपके पास क्या आ गया, मोलर मास आ गया। मोलर मास कितने आ गया आपके पास, 12 आ गया इसका, और प्लस आपने क्या करना है, H2 है, H2 आपके पास है 3 किलो मोल। अगर आप इसको बैलेंस करेंगे इक्वेशन को तो 3 किलो मोल आपके पास H2 है, और आपके पास H2 की मोलर मास 2 आ गई। तो दिस इज द फ्यूल। ओके,
सर ये 3 कैसे आएगा, ये मैं पूछ रहा था।
आपके पास H2, हम लोग क्या करते हैं यहाँ पे देखें ना, आपके पास H2 है और 3 है। ठीक है, आपके पास कितने थे, C2H6 है ना,
यस सर।
तो वहां से आपके पास ये 3 आ गया।
ठीक है सर।
ठीक है, बेसिकली हम लोग बिल्कुल ही एक बेसिक केमिस्ट्री को यूज कर रहे हैं। ठीक है, इसमें कोई इतनी ज़्यादा वो नहीं है कि आपको बिल्कुल ही इसके डेप्थ में जाना पड़े, लेकिन ये है कि बेसिक अंडरस्टैंडिंग केमिस्ट्री इक्वेशंस को डेवलप कैसे करना है, या आप थोड़ा सा अगर रिवाइज कर लेंगे तो ये चैप्टर आसान हो जाएगा समझने के लिए, क्योंकि इसमें सारी बेसिक केमिस्ट्री यूज हो रही है। Okay, so now here it is another question. Okay, so which is also related to your book. Okay, which is 15-31. Okay, so here it is mentioned a certain coal has a following analysis on the mass basis. Okay, so it is mentioned that the fuel is coal and the percentage is given in the form of masses. So 82% of carbon, 5% of H2O, 2% of H2, and 1% of O2, and 10% of ash. The coal is burned with 50% excess air, and you have to determine the air fuel ratio. Okay, so you have to note down the data, then we'll move toward the solution. Okay, so now coming toward the solution. Okay, so in this question it is mentioned we have the mass basis available in the problem statement. Okay, so the equation that we will form. Okay, so for example, first we have to find the number of moles of each reactant products. Okay, so in the reactant, if we can say there is a combustion chamber over there. So this is combustion chamber and this is your products and these are your reactants. Okay, so we are supplying coal and we are supplying air and air is 50% excess air. Okay, so now in the product, it is mentioned in the question we have carbon, we have H2O, we have H2 and we have O2. Okay, and all the percentage which is on the mass basis are given in the question. Okay, so first thing you have to find the number of moles of these uh, all the elements which are present in the product side. Okay, so first thing is you have to find number of mole of carbon. Okay, so number of mole of carbon you can just say that it will be mass of the carbon and molar mass of the carbon. Okay, so mass is mentioned in your question that it is 0.82. Okay, and before this I can just assume over there, so you can just consider that you are burning 1 kg of coal. Okay, so then it will be easy for the analysis purpose. Okay, so then 82% of your carbon is present, so I can just write that it is 0.82 and then you can just divide with 12, which is the molar mass of carbon, and you will get the 0.068. Similar thing, you have to find the number of mole of H2O, which is mass of H2O and molar mass of H2O. So mass of H2O, it is mentioned it is 5%. Okay, so you can just write 0.05 because we are assuming 1 kg of coal divided by 18, and similar thing you will get 0.002. Number of mole of H2 sorry, mass of H2 and molar mass of H2. So mass of H2 0.02 because 2% of H2 is present and you can just divide with the 2, which is the molar mass of H2, and you will get the value of the kilomole, which is 0.01 kilomole. Similar thing, number of mole of O2, which is equal to mass over molar mass of O2. So mass of O2 0.01 divided by 32, which is equal to 3. Okay, so now coming towards the problem. Okay, so in the problem it is mentioned that your coal consists of, if you can just go back to your problem statement. So your coal consists of how many products consist of? So you have to note it down, then I'll move towards the previous slide. I have to find out the problem statement first. Okay, so here it is mentioned that the coal, which is combination of carbon, H2O, H2, O2, and ash. Okay, so for this is our fuel. Okay, so for example, if we want to write the equation, so we can say this is carbon plus H2O plus H2 plus O2 and plus ash. Okay, so this is our fuel, and we have to burn with the excess air, which is 50%. Okay, so it's mean we are going to say 1.5%, 1.5 into stoichiometric coefficient, which is the theoretical air, okay, into air, which is O2, 1 kilomole of O2 plus 3.76 kilomole of N2. Okay, and do not worry about this equation. I will provide this equation in the problem statement each time. Okay, now if you just say that it produces some products, okay, so it produces X mole of CO2, Y mole of H2O, and 0.5 into 8TH, which is the stoichiometric coefficient of O2, and 1.5 into 3.76 stoichiometric coefficient. We have to multiply stoichiometric coefficient into N2 and plus H. Okay, so this is the equation which has become. Okay, so now from the previous side, we have already find the number of kilomole of carbon, number of kilomole of H2O, number of kilomole of H2, number of kilomole of O2. Okay, so you just have to multiply these kilomole with these elements. Okay, so just you have to multiply, and then it will become the complete combustion equation for the analysis purpose of the air fuel ratio. Okay, so if I can just put the value, it will become 0.0683 carbon. Okay, so which we already found in the previous slide, 0.0028 H2O plus 0.01 kilomole H2 plus 0.0031 O2 and plus ash. So now this is our fuel, and we have to, and rest of the equation is 1.5 kth theoretical stoichiometric coefficient O2 plus 3.76 N2, and it's equal to X mole of CO2, Y mole of H2O, 0.5 stoichiometric coefficient O2, 1.5 into 3.76 stoichiometric coefficient N2 plus H. Okay, so now here first thing is you have to find all these values X, Y, kth. Okay, so you can easily find by using just applying the balancing of carbon H and O2. Okay, if I can just apply the balancing of carbon by using this chemical equation, so it turns out to be 0.0683 is equal to X. Okay, so now X is known. So similar thing I will apply balancing of H. Okay, so it will be equal to 0.0028 into 2. Okay, so plus 0.01 into 2 is equal to 2y. Okay, so from here I can easily find the value of y as well. So y is equal to 0.0128. Okay, so you have to note now and move towards the next thing where we have to find the ATH value also, which is stoichiometric coefficient. So similar thing, if you can just apply for the balance of O2, you will get 0.028. Okay, so you just have to correlate with the previous chemical equation. Okay, divided by 2 because it is a monatomic oxygen on the with the H2O. Okay, so then plus 0.031 plus 1.5 into stoichiometric coefficient, and it is equal to x plus y by 2 plus 0.5 into stoichiometric coefficient. Okay, so now we have the value of x and y with us from the previous slide. Okay, so you just have to plug the value of x, which is equal to 0.0683, and you have to plug the value of y, which is equal to 0.0128. And if you can solve this equation, you will get the stoichiometric coefficient, which is ATH, and its value is 0.073. Okay, so now you just have to plug all these values and you will get one equation. Okay, so which is the starting point for finding the air fuel ratio. Okay, so if I can just have to make equation, so it becomes 0.0683 carbon plus 0.028 H2O plus 0.01 H2 plus 0.00031 O2 plus ash. Okay, so here is the fuel, plus you have to burn with the air. Okay, so air by using ATH value, so you just have to multiply 1.5 with the stoichiometric coefficient and you will get which is 0.1095 O2, 1 kilomole of O2 plus 3.76 kilomole of N2, and it turns out to be 0.0683 CO2 plus 0.0128 H2O plus 0.0365 O2 plus 0.4117 N2 and plus ash. Okay, so now this is the equation for the chemical reaction for the combustion process. Okay, so from here you can easily find the air fuel ratio. Okay, so air fuel ratio, you already know it will be equal to mass of air over mass of fuel. Okay, so now here we are analyzing air fuel ratio in terms of kg per air per kg fuel. Okay, so now here we can just simply use mass of air. Okay, so which is you can easily find by using the number of mole of air into molar mass of air. So number of mole of air is 0.01095 into 4.76 and into you have to multiply 29. Okay, so now if you can just multiply, it will be equal to 15.1 kg. Okay, so now we have value of Ma. Okay, and we already assumed during the start of our problem that mass of fuel is equal to 1 kg of coal. Okay, so that we are burning with the air. Okay, so here you just have to simply divide these two terms and you will get the air fuel ratio. Okay, so if you can just divide 15.1 over 1, because we are assuming that 1 kg of coal is we are using, so we get the air fuel ratio as 15.1 kg per air, kg per fuel. Okay, so this is the solution for this type of question. If we have the coal, because coal percentage is not known to us specifically, there is percentage of ash as well. Okay, so here we have to assume that we are burning some specific amount of coal. Okay, so it is not mentioned, so you have to choose what amount of coal you are. Okay, but you have to specify the assumption first. Okay, so you have to note it down and move towards the next question. Another question, which is your example 15 dashboard from your book. Okay, so here it is mentioned that the octane is burned with dry air. The volumetric analysis of the product on dry basis is given. Okay, so your percentage of CO2, which is in the product, O2, CO, and N2 is mentioned. Okay, so your main target is to find the air filtration and percentage of theoretical air used. Okay, so this is the question. You have to note it down and move towards the solution. Okay, so now based on this data, we can develop one equation which is x number of C8 H18, which is the fuel, and we can say it will be, you can just denote with any number, a number of air O2 to 3.76 N2, and it gives 10.02% of CO2, okay, which is mentioned in your problem statement, plus 0.88 carbon monoxide, plus 5.62 O2, plus 83.48 N2, and plus you can say B H2. Okay, now this is the question. Equation. This equation will be given in the problem statement whenever it will be your test exams. Okay, so now here, first thing we have to apply the balance for in order to find the value of a, in order to find the value of x, and also to find the value of b. Okay, so we can simply say that first we can apply the balance for n2. So for n2 balance we can 3.76 a is equal to 83.48, and here we can easily find the value of a, which is equal to 22.2. Similarly, we have to apply for the balance of carbon. So 8x is equal to 10.02 on the product side and plus 0.88 on the product side. Okay, so you get the value of x, which is equal to 1.36, and similarly you have to apply for the balance for h. Okay, so you will get the value of b as well. So if we apply the value of h balance, we can say it will be equal to 18x, which is equal to 2b. So x value is known to us, so simply we can find the value of b, which is equal to 12.24. Okay, so now we have all the value which is required in the equation to find the combustion equation. Okay, so simply you can apply, put the values, which is 1.36 C8 H18 plus 22.2 O2 plus 3.76 N2, and it's equal to 10.02 CO2 plus 0.88 carbon monoxide plus 5.62 O2 plus 83.48 N2, and plus you have B into H2. Okay, so I will just write at above 12.24 H2. Okay, so first thing, before analyzing the air fuel ratio, so you have to just divide all this equation with 1.36. Okay, so that the combustion equation for 1 kilomole of fuel is obtained. Okay, so that you will get 1 kilomole of fuel. So you have to divide 1.36 at all the side, and then your combustion equation will be ready for the air fuel ratio analysis. Okay, so you have to note it down and move to the next slide. Okay, so by dividing 1.36, I get the equation which is C8 H18 plus 16.32 O2 plus 3.76 N2, and it will be on the product side we have 7.37 CO2 plus 0.65 carbon monoxide plus 4.13 O2 plus 61.38 N2 and plus 9 H2. Okay, so now from here, our first part is to find the air fuel ratio. Okay, so air fuel ratio basically is the mass of air over mass of fuel. Okay, so mass of air you can easily find 16.32 kilomole into 4.76, okay, which is the mole of air, and into molar mass 29 kilomole. Okay, so mass of fuel. Okay, so here in the previous question, one student asked that where these moles come from. Okay, so you can just simply use the direct method also. Okay, I think you have already studied in the chemistry courses that if you want to find the number of molar mass of, for example, mass of, I want to find the mass of fuel. Okay, so it is equal to number of mole of fuel into molar mass of fuel. Okay, so rather than you have to just divide all the components, so you can directly use. So here it is number of mole of fuel is 1, and you directly multiply with the molar mass of total fuel. Okay, so molar mass of total fuel is I think 12 into 8 and plus 18 into 1. Okay, so you just have to divide this value and you will get the, okay, so if anyone calculate it, it will be equal to, okay, so it is 114. Okay, so you can just directly use this method also. Okay, rather than you have to divide, separate all the component and find the number of mole and then add it. Okay, so this is another method for finding this. I think this is more easy for you. So 19.76 kg of air per kg of fuel. Okay, so this is another thing you have to consider for finding air fuel ratio. If you have any question, you can also ask.
सर ये 4.76 कहाँ से आया?
जी कौन सा 19.76?
4.76.
Okay, 4.76 basically, I already told you that we are considering 1 kilomole of O2 and 3.76 kilomole of N2. So you have to divide 1 plus 3.76. So it will be 4.76. Okay, so this is the standard form of air. Okay, so whenever we are saying in the combustion process we have supply air, okay, so you have directly say that it will be 1 kilomole of O2 plus 3.76 kilomole of N2. Okay, so this we already discussed in the first slide as well of this lecture. So this is equal to the dry air. Okay.
Yes, sir.
Okay, although air is a combination of many other elements as well, because there are neon, there are other many gases. So for our simplicity, for the combustion analysis process, we just say that it consists of only O2 and N2. Okay, so now in the part B, okay, so part B, we have to find percentage theoretical air. Okay, so for percentage theoretical air, so first thing is we have to know the theoretical combustion equation, because previously which equation we already developed is basically the actual combustion equation. So first we have to determine the theoretical combustion equation. Okay, so this equation I will also provide in the exam also. Okay, during if you find any problem related to this. So for example, the theoretical equation, theoretical combustion equation is ATH O2 plus 3.76 N2 which is equal to 8 CO2 plus 9 H2O plus 3.76 stoichiometric coefficient into N2. Okay, so if you can compare both of these equations, you can easily find the difference that we do not have O2 in the products for the theoretical combustion equation. Okay, so this we already discussed whenever we are talking about theoretical or stoichiometric equation. So there is no O2 present in your product side. Okay, and also if you can notice there is no carbon monoxide as well. Okay, so this is how we can generate the stoichiometric equation. So this equation I will provide in your exam as well. Okay, whenever you can see this type of question. So here you first have to find the stoichiometric coefficient, which is 8 plus, okay, so you just have to balance it. So it will be 8 plus 4.5 by doing the O2 balance, which is equal to 12.5. So here we can easily find the percentage of theoretical air. So I can just write the percentage, and you can get theoretical air, which is equal to mass of air, and you can say it will be actual over mass of air theoretical. Okay, so mass of air actual come from your previous equation, which we already developed in the previous slide. Okay, so if you can just go back to your previous equation, you can easily say that number of mole of air into number of molar mass of air over number of mole of air and molar mass of air. Here we have actual, and here we have theoretical. Okay, so now here molar mass of air can easily be eliminated because molar mass for actual or theoretical air is the same. Okay, so here we are dealing with the number of mole of air for the actual and number of mole of air for the theoretical. So number of mole of air for the actual you can easily get from the previous equation, so 16.32 into 4.76. Okay, so you just have to go back to and see the equation which you already developed in the previous slide, and the theoretical number of mole come from this equation. So you just have to multiply 12.5, so which is 88 H into 4.76. Okay, so this is your theoretical number of mole. Okay, so here if you can just divide, it will be equal to 131%. Okay, so it's mean we are 130%, 131% theoretical. So we are supplying 31% of excess air. Okay, so this is the meaning of this statement. Okay, so if you have any question, you can ask me. Okay, so now here are some important points over there. Okay, so predicting the composition of product is relatively easy when the combustion process is assumed to be complete. Okay, with the actual combustion process, it is impossible to predict the composition of product on the basis of mass balance alone. Okay, so then the only alternative we have to measure the amount of each component in the product directly, and how we have to find the mass balance alone. Okay, so how we have to find the composition of the product on the basis of mass balance. Okay, so we have to use Orstad gas analyzer for this purpose, by using which we have to measure the amount of each component in the product directly. Okay, so this is another method for finding the experimental method, basically Orstad gas analyzer. We can say Orstad gas method. Okay, so this is just for your information purpose. If you can find any MCQs related to this, so you can easily find out that which analyzer we are talking about. Okay, so now we are coming towards another topic, which is related to the combustion process as well. Okay, so enthalpy of formation and enthalpy of combustion. Okay, so we already know that when we are dealing with the chemical reactions, okay, so there's molecules in the system. Okay, and molecule of the system possess energy in various forms, and which include sensible and latent energy, which is associated with the change of state, chemical energy, which is associated with the molecular structure, nuclear energy, which is associated with the atomic structure. Okay, and during a chemical reaction, some chemical bonds that binds the atom into molecules are broken and new ones are formed. And the chemical energy associated with these bonds in general is different for the reactant and the product. Okay, so that's why if, in the reactant and product energy is different. Okay, so then we have something from which we have to represent these energy. Okay, so that's why we have to use specific terms, enthalpy of formation and enthalpy of combustion. You will see the exact definition as well in the next. Okay, so now we already know that whenever there will be a existing chemical bond are destroyed and new ones are formed during the combustion process, so either a large amount of energy is absorbed or released, an energy change of a system during a chemical reaction is due to change in state, okay, pressure and temperature. So here we are specifying that state what we are talking about, and a change in chemical composition. So simply we can say that change in internal energy of your system is change in internal energy of change in energy of state and change in energy of chemical composition. Okay, so when the product formed during the chemical reaction during a chemical reaction exit the reaction chamber at the initial stage, the reactant delta E state is zero, and the energy change of the system in this case is due to change in its chemical composition only. So now here comes towards the actual definition of enthalpy of formation that why we have to use it. So the standard enthalpy of formation is the change in enthalpy that coexists with the formation of one mole of compound from its element, and then the standard enthalpy of reaction occurs in a system when one mole of matter is transformed by a chemical reaction. Okay, so from here you can easily judge that standard enthalpy of formation when we are talking about, for example, if we have in the reactant side we have carbon, okay, and in the product side we get the CO2, for example. I'm just giving the example. So here, because okay, so there is a formation of one mole of compound from its element. So if we can just assume that there is a formation of one mole of compound from its element, so we can just represent with the enthalpy of formation. Okay, so in the similar way, for example, if we say that there is a burning of 1 kg of fuel and it converted into some other form of product. Okay, so then here it comes towards the enthalpy of reaction. Okay, so these two terms we will discuss in detail also in the later slide. Okay, so just for your initial understanding that what is the enthalpy of formation and enthalpy of reaction. Okay, so when we are dealing with the enthalpy of reaction and enthalpy of formation, so first thing is there is a standard reference state. Okay, so in thermodynamics, any state as a reference state can be chosen and assign a value of zero to the internal energy or enthalpy of a substance at that state. After the system undergoes a process, the energy changes of a system is evaluated during that process by comparing it with the reference state. Okay, so in the thermodynamic analysis, the chosen reference state for reacting system, we're talking about the combustion process, is 25 degrees Celsius and 1 atmospheric pressure, which is known as the standard reference state. Okay, so the meaning of this is that, for example, if we have to analyze some property, for example, enthalpy of formation for some specific point, for example, if we have some value at 500 Kelvin, okay, so we have to compare with some reference point as well. Okay, so that we will get understanding what is the change of enthalpy from that state to the final state. Okay, so this is the meaning that we have to choose one reference point so that we can compare with it the values. The property value at the standard reference state are indicated by subscript this small o such as HO and U. Okay, so this you can easily find out that if we have mentioned that H naught or U naught, so it's mean we are talking about standard reference state. Okay, and standard reference state at 25 degrees Celsius or 1 atmospheric pressure. And when analyzing the reacting system, the property value relative to standard reference state must be used. However, it is not necessary to prepare a new set of property table for this purpose. So the existing table can be used by subtracting the property value at the standard reference state from the value at the specific state. Okay, so here is the example for all the story which is written over there. The ideal gas enthalpy of, for example, N2 at 500 Kelvin relative to standard reference state. So, for example, we have to find the ideal gas enthalpy of N2 relative to standard state. So we can just say that. Okay, another important point is whenever it is mentioned at H bar. Okay, so it's mean we are talking about kilojoule per kilomole. Okay, if it is simple H, it's mean it is kilojoule per kg. Okay, for the enthalpy. So here we have H bar 500 Kelvin. So here is enthalpy is given minus H naught enthalpy, which is at the reference state. So reference state is 1 atm and 25 degrees Celsius. So simply you have to use two enthalpy value, which is one which is at 500 Kelvin and one as a reference point, and you can easily find the enthalpy change by using relative to that standard reference state. Okay, so this is the story which we already discussed about over there. Okay, so this is an example. Okay, so now here again related to the enthalpy formation, enthalpy combustion. So ignoring any work interaction, the heat transfer during this process. Okay, so this all terms you can easily understand when we are going to solve the questions. Okay, so that you will get better understanding of it. Okay, equal to the difference between enthalpy of product and enthalpy of reactant. Okay, so just simply you can say that the heat transfer during the process is equal to enthalpy of product minus enthalpy of reactant. And minus sign, it's mean that we are that energy is released during this reaction, and it is an exothermic reaction when we are representing with the negative sign. So since both the reactant and the product are at the same state, the enthalpy change during this process is solely due to change in chemical composition of the system. This enthalpy change is different for different reaction, and this property represents the changes in chemical energy during a reaction. Okay, so now here comes terms enthalpy of reaction. Okay, so basically enthalpy of reaction is defined as a difference between the enthalpy of the product at a specified state and enthalpy of reactant at the same state of the complete reaction. So here it is mentioned Q, so you can just say that it is equal to HR. Okay, so the enthalpy of reaction and the Q basically the same thing. Okay, and we can represent with the bar over there, that is kg per kilomole. Okay, so now for the combustion process, the enthalpy of reaction is usually referred as an enthalpy of combustion. Okay, so enthalpy of combustion and enthalpy of reaction basically the same thing. Okay, so here it is mentioned also that HR is equal to HC is equal to H of product and enthalpy of product and enthalpy of minus enthalpy of reactant. Okay, sometimes it is mentioned that enthalpy of reaction is given in your question, so you can easily find out that we are talking about the enthalpy of combustion. Okay, so these two terms will be used. So enthalpy of combustion of a particular fuel is different at different temperature and pressure. Okay, so now there are so many different fuels and fuel mixture that it is not practical to list HC value for all the possible cases. Okay, so moreover, the enthalpy of combustion is not much useful in the case of incomplete combustion. Okay, so it is more practical to have a property representing the chemical energy of the element and compound due to its chemical composition at a specified state in comparison to reference state. Okay, so now here we can define the enthalpy of formation, which you already discussed in the previous slide. That HF, which is, and we have to represent enthalpy of formation by HF, is defined as enthalpy of substance at specified state due to its chemical composition. Okay, and by analyzing the combustion analysis, combustion equation or combustion problem statement. Okay, so first thing you have to know that to establish at a starting point the enthalpy of formation for all stable element such as O2, N2, H2, carbon is assigned a value of 0. Okay, so for example, if I can say that you have to find the enthalpy of formation for the reactant. Okay, and in the reactant there is O2, N2, H2 and carbon is present. So simply you have to assign value 0 for these enthalpy of formation. Okay, so this is the starting point for the analysis purpose. The enthalpy change during the formation of CO2 from its element carbon O2 at 25 degrees Celsius and 180 atmospheric during the steady flow process was determined to be minus 393,520 kilojoule per kilo. Okay, so this is just example that we are going to in the reactant side. We have carbon 1 kilomole and O2 1 kilomole. Okay, in the combustion chamber we have to react it and we get the CO2. Okay, so here energy is released because it is the exothermic reaction. So it is minus 393,520 Q. Okay, and here we represent with the enthalpy of formation. Okay, because here if you can notice that we already talked about that enthalpy of formation is when the elements make some compound over there. Okay, so that is the meaning of enthalpy of formation. Okay, and if for example, if in the same equation we have O2, we have N2, we have H2. So for just for example, and carbon. Okay, so simply if I have to find the enthalpy of formation of the product. Okay, so simply these values are 0. Okay, because here we have mentioned that as to establish a starting point, we have to assign enthalpy formation for all stable element assigned to value of 0. Okay, so this we will see in the problems as well. Okay, so we will discuss some problems related to. Okay, so this thing we already discussed about it, so you have to go through it by yourself. Okay, that the combustion of carbon is an exothermic reaction and reaction during which chemical energy is released. Okay, so here it's also the same point. The negative enthalpy of formation for a compound indicates that heat is released during the formation of that compound from its stable element. Therefore, the endothermic process has a product having positive enthalpy of formation, and exothermic process has a product with negative enthalpy of formation. So, and these enthalpy value, HF value, and you can easily find the thermodynamic table as well. So we will discuss for that tables also. Okay, so now here another important parameter which we have to use while analyzing the combustion equation is the heating value. Basically, heating value and your enthalpy of combustion is almost the same thing. Okay, heating value, whenever we have to say that enthalpy of formation, we represent it with the kilojoule per kilomole. Okay, however, whenever we are saying heating value, so heating value is mostly in kg, kilojoule per kg. Okay, and heating value of the fuel is defined as the amount of heat released when a fuel is burned completely in a steady flow process and the product are returned to the state of the reactant. Okay, so sometimes we can represent with the that this is the heating value of fuel is, and heating value is only defined for the fuel. However, enthalpy of combustion is defined for any substance. Okay, so this is the main difference between the enthalpy of combustion and heating value. And the heating value of fuel is equal to absolute value of the enthalpy of combustion of the fuel. Okay, so these are all things we already discussed: enthalpy of reaction, enthalpy of combustion, enthalpy of formation. Okay, so this you have to go through it by yourself. And then there is a heating value, the amount of heat. Okay, so now here another important point is, because we have two different heating values. Okay, so heating value we already discussed, that amount of heat released when fuel is burned completely in a steady flow process and the product are returned to state of reactant. The heating value of fuel is equal to absolute value of enthalpy of combustion of the fuel. Okay, so now here we have another term, high heating value and low heating value. Okay, so for example, if you have a fuel and there is air and you are burning in a combustion chamber, okay, and some energy is released and it's a exothermic reaction. Okay, so in the product we have H2O. Okay, and if this H2O is in the form of vapor, okay, so it's mean that it is called as a lower heating value. Similarly, if it is in the form of liquid, it is called as a, when the H2O in the product is in the liquid form, we define as a higher heating value. Okay, so this is the main difference between higher heating and lower heating value. It's only depend upon the phase of H2O in the product. Okay, so we will discuss about it when we are solving the problem, so that you will get better understanding of it. Okay, then how to present correlate low heating value with the high heating value? So it is using by simple equation. So high heating value is equal to lower heating value plus mass. Okay, so here mass is basically, we are talking about mass of H2O, which is in the product side, and plus HFG, which is, we already know that it is the value of, we can easily find in the thermodynamic table as well. Okay, so high heating value of fuel is equal to the sum of lower heating value of the fuel and the latent heat of vaporization of H2. Okay, so this is the heating value. Let's see, we can represent in kilojoule per kg of fuel, and simply high heating value is equal to lower heating value plus m into HFG H2O. Okay, and for fuel with variable composition, for example, coal, natural gas, fuel oil, and the heating value may be determined by burning them directly into the bomb calorimeter. Okay, so this is the experimental way to find the composition of this type of fuel. Okay, I know, because this is a very theoretical type of topic, so it is more boring type of lecture. Okay, but you have to go through these all terms by yourself after this lecture, okay, so that you will get some understanding of it. Okay, so now here, whenever we have to talk about enthalpy of formation, we have to consider two tables. Okay, so table A26 and table A27. Okay, so we will see that the tables also. Okay, so there is table 826, which is enthalpy of formation. Okay, it is mentioned, and table 827, properties of some fuels and hydrocarbon. Okay, so these tables we can use for finding the enthalpy of formation directly. Okay, and sometimes we have to use for solving some problems as well. Okay, so we can simply go to table. Okay, so here is table 826. So for example, if you want to find the enthalpy of formation for carbon, hydrogen, nitrogen, Okay, so you can simply say that oxygen we is mentioned is 0. Okay, then carbon monoxide, carbon dioxide, water. Okay, so all the values of enthalpy of formation is known to us by using this table. Okay, then most frequently we use also these type of element only for the analysis of combustion process. Okay, similarly in the table 827, we have the values of high heating value and low heating values. Okay, so if you have to find the carbon high heating value, you can easily go to the thermodynamic table 827, and similarly for the lower heating value, you can also easily go to table 827. Okay, so this is the procedure for finding some parameters related to the combustion processes. So if you have any question, you can also ask. Okay, so here comes towards an example. Okay, so this is example 15-5 from your book. Okay, so determine the enthalpy of combustion of a liquid octane, okay, C8H18 at 25 degrees Celsius and 1 atmospheric pressure using enthalpy of formation data from table 826. Assume the water in the product is in the liquid form. Okay, so you already know that it's a liquid first, so it means that we are talking about the higher heating values. Okay, so you have to note down the data and then move towards the solution. Okay, so in order to start, okay, so first we need the value of enthalpy of formation for CO2, okay, for H2O as well, okay, because CO2 and H2O is in the product side. Okay, so you have to simply go to thermodynamic table and find the enthalpy of formation of okay, so 26, A26. So first thing you have to note on the value. So if I can write the value of for CO2 first, okay, so CO2 value is mentioned at here. Okay, so minus 393,520. Okay, so you have to note which is enthalpy of formation and minus 393,520. Similar thing, you have to note the value of H2O. Okay, so here H2O and here it is mentioned it is in the liquid form. Okay, so H2O value liquid minus 285,830. Okay, now third element which is Ca-14. Okay, so which is the fuel. Okay, so for C8H18, so simply you have to. So here it is mentioned and it is minus 249,950. Okay, so now coming towards the problem again. Okay, so now HF values for these CO2, H2 and C8H18 are known to us from thermodynamic table. Okay, so now by using the combustion equation, so simply I can write this combustion equation C8H18 plus stoichiometric coefficient O2 plus 3.76 N2 give 8 CO2 plus 9 H2O into liquid and plus 3.76 stoichiometric coefficient into n. Okay, so this is the equation. Okay, so our main thing which we have to determine is to determine the enthalpy of combustion of liquid obtained C8H18 at 25 degrees Celsius and 1 atmospheric pressure. Okay, so this is our required thing which we have to. Okay, so enthalpy of combustion we have to find. Okay, so enthalpy of combustion you already know, which is equal to enthalpy of product. So here we are talking about an H of reactant. Okay, so now here we can easily write that summation of number of mole into HF. Okay, and here bar for the kilojoule per kilomole. Okay, and number of mole I have just multiplied, because similar thing if you have to find in form of kilojoule per kg, you have to multiply with the mass. Okay, so here I just multiply with the number of moles. Okay, so similar thing summation of. So here I am talking about products and minus summation of number of mole for the reactant and enthalpy of formation for the reactant. Okay, so now we have the enthalpy of formation for both products and reactant with us. Okay, so simply you have to put the values. Okay, so for example, I can write that number of moles into enthalpy of formation of CO2, okay, which is in the product. Okay, so similar thing I can also say that plus you have to number of mole enthalpy of formation into H2. Okay, this is also in the product side. Okay, so now I have to minus number of mole into enthalpy of formation for C8H18. Okay, so why I did not use the value of O2, N2 and N2 in this equation? So we already discussed in the previous slide that enthalpy of formation for all the O2, N2 stable substances are 0. Okay, so these enthalpy of formation are automatically 0. Okay, so that's why I didn't add these values in this equation for the enthalpy of combustion. Okay, so now simply you have to multiply the number of moles. Okay, so the number of moles is 8 moles for CO2. Enthalpy of formation of CO2 is minus 393,520, which comes from thermodynamic table. Number of mole of H2O. So you have to find out in this equation, which is 9. And enthalpy of formation for H2O minus 285,830, and minus number of mole of C8H18. Okay, so which is 1 kilomole, and enthalpy of formation minus 249,950. So this comes from thermodynamic data. Okay, so if you can solve it, you will get the value of enthalpy of combustion. Okay, so which is the required thing in your problem statement. So it will be equal to so it will be equal to, if you can solve it, it will be equal to 1 minus 54710 kilojoule per kilomole CaH18. Okay, so this is the required thing which we have to find by using this data, which is to find the enthalpy of combustion. Okay, so if you have any question, you can ask me, and this is the required thing. And if you can convert it into the kilojoule per kg, so simply you have to divide with the molar mass, so it will be equal to minus 47891 kilojoule per kg of CaH18. Okay, so you can write in both the terms, in terms of molar mass also, in terms of mole, kilomole, and also in terms of kg. Okay, so if you have any question, you can ask me. Okay, and okay, now here important point that because it is mentioned in your problem statement that H2O is in the liquid form. Okay, so if it is in the liquid form, so enthalpy of combustion associated with this is equal to higher heating value. Okay, so for example, if I can say in the problem statement, you have to find the higher heating value. Okay, so simply you have to note down the value which is equal to minus 47891. Okay, so higher heating value and enthalpy of combustion is equal over there. Okay, so if it is in the liquid form, if it is mentioned it is in the gaseous form, okay, so then it will be equal to lower heating value. So I hope there will be no question. Okay, so now at this point we will stop, and you have to solve one question by yourself. Okay, so only the thing which you have to change is that rather than H2O liquid, so you have to choose H2O as a gaseous in the uh, product side. Okay, so again the problem is the same. So you have to determine the enthalpy of combustion of liquid octane. Okay, and just by considering that H2O and the product side is gaseous instead of liquid. Okay, so if you have any question, you can ask me, and all the students will get 0.2 absolute